Sorry for the quick cutoff in that first part, but as we were talking about, interactions can be affected by things like abiotic factors, and a lot of other things can actually affect the strength of an interaction. Okay, so here's an example of sea stars in the genus Pisaster that prey on mussels, which are these mollusks that live along rocky intertidal areas like in this beautiful beach in Oregon here. And to demonstrate the fact that the effect that this predator, these sea stars, have on this prey, these mussels, and how strong that interaction is, we do what kind of studies? Everybody should be saying it out loud. We do removal studies, right? So one of the ways that we can remove the sea stars from the situation is to build some cages that exclude sea stars and then look at the relative population sizes of the mussels that live in different areas along the zone here. So what you can do is ask the question, how strong is the predation on the mussels? So then one of the things that you can see is whether or not the interaction strength is affected by other kinds of abiotic factors, such as the exposure to waves. Okay, so we can look at the effect of this exposure by putting the cages in wave protected areas and putting some cages in exposed areas, and then seeing what the interaction strength is. And so we can clearly see in this example that the strength of the interaction, that is the strength of the predation in affecting the abundance of the mussels, is stronger in the protected areas than it is in the exposed areas. So what is this saying? In areas that are exposed to a lot of wave action, perhaps this abiotic factor is stronger or just as strong as the predation is on the mussels, again in controlling mussel density. When we did the case study on coyotes in class, we were talking about species like keystone species and dominant species, and I just want to review that here. So dominant species are those species that have a large effect on other species within a community and can influence species diversity. And this is by virtue of just their sheer abundance or biomass. So there's just dominated by that kind of organism within a community, such as trees. A forest is just dominated by trees, or coral reef ecosystems are dominated by corals. So the abundance or biomass of the species is what's having such a big effect on the community. And this is in contrast to what we call these keystone species that have a strong effect on communities because of the roles that they play. So they may not be in very high abundance, right? Their effect is in large proportion relative to their biomass or abundance. Okay, so the sea stars that we were just talking about are a good example of a keystone species because they're not necessarily more abundant than the other species, but because they have such important roles via these trophic interactions, they're such important predators, they have large effects on the overall community structure, again, in terms of species diversity. So other species such as sea otters and beavers can also be keystone species in having these strong effects, but not necessarily because of their abundance, but definitely due to their trophic interactions. This slide just presents a graphical representation of what we were just talking about, the relative abundance and biomass of each species compared to their total effect. Okay, and so dominant species, you're going to see this linear relationship where you've got dominant effects of things like corals and trees, and keystone species may have relatively low abundance but high effects. And here we have high abundance, high effects. So we see this relationship here. Sea stars in the genus Pisaster are definitely famous for their keystone effects in communities. And you can see Pisaster here at the top of some trophic interactions where they feed on some mollusks like Nucella. They also feed on limpets, they feed on chitons, they feed on bivalves, which are also fed on by this intermediate predator here. They feed on barnacles. And so what's interesting is if you remove Pisaster from the system, the community goes from having about 15 different species in it to only 8 species. And you can ask the question, why does removing this top predator make the species diversity of the community decline? So think about the answer to that question and think about the role of competition in the answer to that question, right? Because the fact that you have, when you remove a predator, what's going to happen to the abundances of the prey species? And then therefore, what's going to happen to the strength of the competition amongst those prey species? And that may give you the answer to why we see the community dropping from 15 to 8 species in the absence of this keystone predator. Another categorization of species that are important in ecosystems are what are known as ecosystem engineers. So those kinds of species that are in this category, they may also be dominant species like trees, or they may also be keystone species like beavers. But engineers are those species that can create, modify, or maintain physical habitat for themselves and other species. What do we mean by this? Well, if you think about a tree, it's doing a lot within those communities. The tree leaves and branches provide habitat for other species to live in. Tree leaves fall to the floor, and this leaf litter in the forest floor provides all kinds of habitat, as well as adding nutrients to the soil so that other organisms can live there. The tree roots will aerate the soil. They bind rocks together. They stabilize the forest floor. Fallen logs provide space, nutrients, moisture for seedlings, as well as habitat for other species. The trees, just by virtue of their shade and retaining moisture, affect the abiotic factors within the community. So trees have an enormous effect on controlling the properties within a community, and therefore, again, we call them ecosystem engineers as well as dominant species. Beavers are also ecosystem engineers as well as keystone species, as we mentioned before, meaning that if you remove them from a system, they have large effects on a community, even though they're not that abundant themselves. But they also behave in such a way that they can create networks of wetlands. As you know, beavers build dams, and they can dam up the water systems of flowing water and therefore create wetlands in different areas. And these maps show how the overall percentage of wetland and changes in stream flow can occur over time just with the presence of beavers from 1940, from 1961 to 1986, the extensive network of wetlands that are created by beaver populations in particular areas. If any of you have just walked in the woods in the area around here, like when we were out at Goose Pond, you can see the evidence for beaver activity everywhere. You just walking along the edge of the pond or edge of the streams, you can see trees or tree trunks that have been chewed on by beavers. Beavers are very common in New England, and I encourage you to take a walk and look for beaver activity and think about their importance both as keystone species and as engineers of the ecosystem. I want to focus on now another really important topic in community ecology, and that is the ways in which communities are changing. Communities are always in a constant state of change, even though they may change on timescales that seem slower than we can observe as humans. But human actions are becoming one of the strongest forces behind community change. Okay, so we know that species interactions such as competition, predation, disease, all of these things can affect the gradual replacement of species over time. And certainly changes in abiotic conditions such as sea level, water temperature, all of these can cause physiological stress, and in a marine ecosystem they can cause coral bleaching, eventually mortality, and then finally catastrophic disturbances such as tsunamis. And we've been certainly hearing in the news about typhoons and hurricanes lately, and these can cause massive changes in communities such as coral reefs as well. But in spite of these natural phenomena such as species interactions, changes in abiotic conditions, and catastrophic disturbances, again, all of which can occur naturally, the effects of human interventions within systems like coral reef communities are even much more have a much greater impact on these communities and have a much higher effect of what we call disturbances within communities. But focusing on natural processes for a moment here, abiotic agents of change can fall into two main categories, those that we call disturbances, as I was just talking about, as well as what we might call stresses. And you might recall that we talked a bit about this way early on in the beginning of the semester when we were talking about tolerance versus avoidance strategies. But disturbances are events that kill or injure individuals and create opportunities for other individuals. So disturbances basically affect survival, okay? And stresses, on the other hand, can reduce growth or reproduction of individuals. Okay, so that there's not necessarily a distinction that's always made completely between these two. And we've talked about this before over and over again, that these words give us some language, a common language to talk about phenomena, but we don't have to split hairs over everything. Okay, so examples of abiotic factors and agents of change that can affect organisms include waves, wind, water supply, chemical composition, temperature, volcanic activity, and the effects are shown in this table here, that organisms can become detached or injured, organisms can grow slowly or injured, and things like hurricanes, floods, tsunamis, droughts, mudslides, pollution, acid rain, freezing snow, ice, avalanches, hot gases, mudslides. And then we've got biotic factors down here that can cause negative interactions for some species, competition, predation, herbivory. Okay, so all of these kinds of things are examples of abiotic and biotic agents that can affect organisms within ecosystems. The important thing about disturbances is that they can allow other organisms to come in when a community has been completely disturbed and is, even in some cases, all the way to the point where no life is there anymore, and then now there's opportunities for new life to grow in an area where once it wasn't before. And the example of a volcanic eruption such as Mount St. Helens in Washington State that you guys may be somewhat familiar with because it happened fairly recently within our time and gave scientists an opportunity to study the effects after the volcanic eruption in what happened to the surrounding community. This diagram shows the extent of the damage from the point of the initial eruption here, and then the places that were called the blowdown zone, just from the force of the explosion and a lot of the vegetation that was blown down. Scorch areas that were scorched by the lava flows. You have this dome of lava over here, the mud flow zones here, the pumice plain where the high amounts of hot lava flowed out here. There's debris that avalanched down. So again, there's a really large area that was affected by the eruption of this volcano. And by transforming the living community into nothing that was living for a while, again, gave us a chance to sort of look at how do organisms come back in, how do they recolonize areas, how do communities change over time when they're sort of set back to square one or set back to point zero. And these changes over time are what we call succession. This slide just shows some photographs of those areas that were mentioned in the previous diagram. So you can see the scorch zone, blowdown zone, debris avalanche, and the pumice plain here.